Today we're going to take the product from our previous video, hypophosphorous acid, and use it together with iodine to reduce a secondary alcohol. The mechanism of this reaction is complex, but hydriodic acid is produced as an intermediate and this is the active species. The secondary alcohol we're going to use is mandelic acid, also prepared in one of our previous videos. We weighed out 10 grams of mandelic acid crystals as you can see here. For details about how to synthesize mandelic acid, check out our other video linked here. We set up a 250 ml flask equipped with magnetic stirrer, and added the dry mandelic acid to the flask. Then we got a small amount of cold water, about 10 ml, and slowly added this dropwise with stirrer to dissolve the acid. We added just enough to make a stirrable slurry. Not all the acid dissolved. Here's our slurry. Our idea was not to add too much water at this point so as to dilute our hypophosphorous acid too much. Now we measured out 15 ml of our approximately 70% hypophosphorous acid solution that we prepared in the previous video. This is a large molar excess to the mandelic acid in order to speed up the reaction. We added this to the flask. You can see that the acid is quite viscous and syrupy. Together the water and the acid very nearly dissolved the mandelic acid, but there were a few lumps floating around so we added another 5 ml of water to get these to dissolve. Perfect! We took the flask and placed it into a cool water bath at around 10 degrees C. We saw how our phosphorus acid reacted with iodine in the previous video, and we didn't want a repeat so we figured that cooling the mixture would help keep things under control. Now for the key reagent. We weighed out 20 grams of solid iodine. This is approximately the same molar amount as the hypophosphorous acid. We're using commercial iodine here, but if you want details about how to make solid iodine then check out our other video linked here. To begin with, we added a very small amount of iodine to the reaction flask, just to see if there would be any fireworks. With stirring on, the iodine mixed around in the solution and the mixture turned a yellow color. But no rapid reaction. So we continued adding the solid iodine slowly to the mixture, and we started to see it dissolving and forming a brown color. And after a few minutes the brown color disappeared again to leave the yellow solution with the iodine dissolved completely. So we added the remainder of the iodine and allowed it to dissolve in the reaction mixture. Here we go. Everything now in solution. What has now happened is that the iodine has been reduced to hydriodic acid, which is now dissolved in the aqueous reaction mixture. We removed the water bath and placed the flask on a hot plate. We attached a reflux condenser circulating cold water and began to heat the flask to reflux temperature. And then we left the reaction flask gently refluxing for 3 hours on the hot plate. Over 3 hours not a lot happened, but there was a strange sulfurous eggy-type aroma coming from the condenser. The reaction mixture became a slightly more pale yellow. Here we are after 3 hours. At this point we took the flask off the heat and allowed to cool before dismantling the apparatus. As the flask cooled down the contents solidified into a crystalline mass as you can see. This was fairly easy to break up however using a spatula. So we got the contents of the flask into a center and filtered using vacuum to drive off all the liquid, and then washed with a small amount of ice-cold water. The water wash removed the yellow color of the crystal. Here's our first batch of product. 5.3 grams of phenylacetic acid crystals. They have a flaky appearance and a beautiful iridescence when light shines on them, a little bit like mother of pearl. The compound has an acacia aroma a bit like a rich sweet honey. Well, this is not bad, but we figured we could probably get some more product out of the filtrate. So we poured it into a separating funnel. And then measured out 25 ml of dichloromethane, which we added to the funnel to dissolve out any residual product. After a good shake, the layers separated nicely, with the top layer being our organic solvent. We drained off the bottom aqueous layer and reserved it so that we could recover the iodine. We'll explain that later. Then we drained off the organic dichloromethane layer into a beaker. And placed this on a hot plate to evaporate the solvent. The result was a syrupy liquid which crystallized as it cooled down. We filtered the crystals and again used a little water to wash them as well as we could. And here's our second batch of product. 1.5 grams of phenylacetic acid. Although not as pure as the first batch, as the crystals are less well formed and slightly discolored. Altogether that's 6.8 grams of product, which is a 76% yield on starting mandelic acid. We're impressed with this reaction and surprised it works so well compared to the traditional red phosphorus method. It's one to remember. The crystals of our product are certainly very beautiful. To recover the iodine is very simple. Take the yellow aqueous layer from the DCM extraction we did. Now make up a solution of ammonium persulfate in water. Use an equal molar amount to the starting iodine. Now add the aqueous solution from the reaction to this. The iodide in the solution will be oxidized to solid iodine, which can be filtered off. Check out our other video for full information on this. Thanks for watching. We'll leave you with a video of the phenylacetic acid in our second batch crystallizing. Stay tuned.